Hey everyone, we're going to continue our discussion by dynamics and talk about the very last law of Newton's three laws of motion. So this one is both extremely important, but at the same time, not super used all the time. This is actually a law that will be mostly used in explanation type questions. So ones where you're trying to explain your reasoning, this is when you're going to start bringing in Newton's third law. It does have a minor effect in some of the math that you end up doing, but it's more of a small thing rather than a grandiose type of calculation aspect. So Newton's third law refers to what's going to happen, where some of these forces come from, and what happens when objects interact with each other. That's really what the idea of the third law is. You've probably heard that, just like with all these other laws, you've probably heard this before. Now let's consider this a case. We have a man that's on a skateboard. He throws a basketball forward towards a friend. Does the man stay still or does he move? And if so, in what direction? So this leads us into Newton's third law, which is for every action there's an equal opposite reaction. If you ever, if you try to consider that, you know that as the person throws the ball forward, then he's going to start rolling backwards on the skateboard. So that idea that the person applies a force onto the ball, that ball that ends up having an equal and opposite reaction and applies a force backwards onto him. So that's the idea of Newton's third law. This is the law of action-reaction pairs, and it basically says that that these forces come into balance. Now, one thing I do want to point out is it doesn't mean that the two forces act on the same object and balance out, but they act on two different objects. So, for example, if I go over to a wall and I push on the wall, I am applying a force to the wall towards it. That wall, however, is going to apply an equal and opposite force backwards towards me. So the only force I experience is the force from the wall pushing me away. The only force the wall experiences is the force that I push towards it. So I just wanted to mention that because a lot of times people mistakenly think that both action reaction forces act on the same object, but that's not the case. Uh, so this basically is the law that allows you to make claims like when someone touches you that they're technically touching you back, or if someone pushes you that they also are pushing you back. This is the law that actually kind of explains how a lot of things work. For example, it explains how we walk. So if you ever try to think about it, the way we walk is by we're pushing on the ground. We push the ground backwards, and in reaction, the ground pushes us forwards. If we drive in a car, the same thing happens with the tires. The tires literally grip the pavement and push the pavement back. The pavement then pushes the car forward. So our action is the tire pushes on the road, and the reaction is the road pushes on the tire. Same thing for rockets. Rockets expel gas out in one direction to propel the rocket forward. Yeah, so this is the whole idea about Newton's third law. You can apply it to almost every single scenario. If you've ever wondered about swimming, the way swimming works is the same thing. You're literally taking water, cupping the water, grabbing onto water, and pushing the water backwards, applying a backwards force to the water, resulting in the opposite reaction happening of the water pushing you forward. This also explains the concept of recoil. So these are all examples. If you've ever kind of seen someone shoot a gun, like in a movie or a cannon, you've always noticed that the object flings backwards, and that's because of recoil. The in here the gun or the cannon or whatever applies a force onto the projectile, pushing it forward. But at the exact same moment, that projectile applies a force backwards onto the object of equal force. And that's why we end up having them go back that way. Now, one thing to clarify is Newton's third law says that the forces are equal and opposite. So the forces on the bullet and the forces on the gun are equal to each other, but in opposite directions. However, the effect of the force is going to be different. The reason I say that is because of Newton's second law, which is F then equals ma. F then equals ma says that the net force is equal to the mass times the acceleration. So even though the forces are the same, because their masses are different, their accelerations will be different. That's why the bullet will end up leaving these guns going at very fast speeds because of the very high acceleration they experience and low mass, while the gun only goes back, at a significantly less speed because it is experiencing much lower acceleration because of its higher mass. So even though the forces are the same, the effects of the force are different. The acceleration they experience will be different. So if a bus is driving on a road and hits into a bug, technically the bug and the bus are experiencing the same force. However, because of their drastic difference in mass, the bug experiences a significantly higher acceleration than the bus, which is why the bug literally explodes as it comes into contact with the bus, while the bus continues as if nothing ever happened, because the acceleration acting on the two objects are drastically different. So let's practice some of the questions. These are going to be some of the more basic type questions. Like I said, you'll see how we're going to apply this in some of the later aspects. In when we start adding in different concepts, in particular, the multi-mass system is kind of where we're going to start bringing this all together. All right, so try this out, and we'll go over in a second. All right, so we have a man pushing on a stroller, and they want us to compare the force exerted on the stroller by the man and the force exerted on the man by the stroller. Now, this is actually a very clear indicator of the Newton's third law, and this is how it appears on the regions. When you kind of have to almost reread the question because the wording makes it sound like it's asking the same thing. That is Newton's third law. So the force on the stroller by the man, on the man by the stroller, same thing. So it is the same. The forces are the same. Okay, we have two cars. And here's the next question. So work on this. We'll go over in a second. All right. So we have two cars, a 1 kilogram object, 2 kilogram object. We have the springs exploding them apart. They say that the force on the 1 kilogram object is 1 Newton, and they want to know what the force is on the 2 kilogram object. Well, because of Newton's third law, it is 1 Newton. All right, here's the next question. Work on this. We'll go in a second. All right. Again, another very common question. So we have the Earth and the Moon. The Earth is 81 times more massive than the Moon, and the Earth exerts a gravitational force of F on the Moon, and they want to know what the force of the Moon on the Earth is. Well, because of Newton's third law, the force is the same. It doesn't matter how massive one object is versus the other, they experience the same force. However, the acceleration will be different. So if we want to compare the acceleration, the moon would be accelerating 81 times more than the Earth because of the force. And I believe this might be the last question, so working this, we'll go over in a second. All right. So this is kind of almost the limit to the way that it gets used in calculations, where you'll be given information about one object. In this case, we're told that the cannonball is 100 kilograms and 100 newtons. And we're told the mass of the we're told that the cannonball is 20 kilograms and 100 newtons. And then we're told information about the cannon. And they want us to find the acceleration on the cannon. And you might think, well, we don't have enough information for this because because Newton's second law that relates force and acceleration requires me to know what the force is on the cannon. But using Newton's third law, we can say, well, since the cannonball experiences 100 newtons, then we know that the cannon experiences that same 100 newtons. So plug in the two numbers in, and we get the acceleration of 1 meters per second squared. Obviously, this is still kind of on the simplistic side, but again, it's kind of more used in explanation reasonings of why certain things are happening. So that's Newton's third law. It's very kind of a quick thing. The whole idea about action reaction, but it does have a lot of ramifications in real world reasoning. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.